Dear students, in this video we'll try to throw some light on the concept of entropy. So, as a matter of information, the word entropy is derived from a Greek word tropos, tropos, and the meaning of the word is in change. So entropy is something which is related to the change or change of state of a system. That is the meaning. So it's actually one of the important concepts in the entire thermodynamics or in physics. And the idea of such a quantity or such a concept was introduced by Rudolf Clausius, after whom the Clausius statement in Second Law of Thermodynamics is known, way back in the year 1865. So the idea to be understood is that the entropy is a mathematical concept. It's quite a mathematical concept, or it's a mathematical device. We can better call it as a mathematical device. Why we just call entropy as a mathematical device? It's due to the reason that unlike other thermodynamic variables like pressure, volume, temperature, energy, etc., entropy is a quantity which is not directly measured, which is not measurable directly by an instrument. I mentioned about this one in the introductory lecture also. So, but introduction of this quantity will be enabling us to answer many of the questions which remained unanswered so far. So, once by introducing this mathematical concept, many of the ideas that were not answered could be answered well, and that's why the entropy assumed relevance. So the credit goes to Clausius to introduce this concept, but later it was just added on by a number of other people. Now, what is the importance? What is the importance of this quantity of entropy? We can use entropy to determine the direction of a process. You consider a thermodynamic process, and see, the process will describe in relation to a system. And if you consider a system to be initially away from its equilibrium state, every system will tend to attain an equilibrium state if it is not initially away from it, right? So you consider any system. So by system you have the definitive meaning, right? So a thermodynamic system, and let me assume that the system is initially not in its most equilibrium state. So left to itself, a system has a tendency to change spontaneously towards its equilibrium state. Okay, now a question arises: what determines the direction of this process? What decides the direction of this process? Why the system is proceeding in a particular direction? Why not another direction? So one thing, qualitatively we say that the system is trying to achieve maximum stability, right? So from unstable to stable, that is the rule. And the stability of a system was so far just related to its energy, right? So stability of a system was so far related to energy, right? So we said that most stable state of the system is a state of minimum energy, or every system tries to minimize the energy of the system. That was our idea. But you will see that there should be something more fundamental. There should be some more fundamental than the energy of the system. As you will see that the law of conservation of energy is not violated in any of the processes. Okay, but in many processes, even though the law of conservation of energy is not violated, certain processes are not found to be occurring in the reverse sense. Whereas, nature, seemingly puts no any restriction on that. So we have discussed some example in our previous sessions, maybe in the previous module. You consider, we will again go to some more examples to cite. Okay, so we considered the cooling of a cup of tea. Hope you remember that was a standard bookish example that you keep a cup of hot tea open in the air. You know that always the cup of tea becomes cooler as time passes. Means heat will be always flowing spontaneously from high temperature to low temperature. Okay, the question is that why not a cold cup of tea getting hot by drawing heat from the surroundings, and we have seen that that principle or that process is not permitted by the second law of thermodynamics. They are only in order to explain such non-occurrence of certain processes, we coined what is known as the second law of thermodynamics. Okay, and second law of thermodynamics was given just in two statements given by Kelvin, Planck and Clausius. So far we couldn't obtain a mathematical formulation. A mathematical quantity couldn't be found out which can represent the second law of thermodynamics. So by introducing the concept of entropy, we could develop a mathematical statement for the second law of thermodynamics, and that is the relevance of the quantity entropy in thermodynamics. So the second law of thermodynamics is helping us to answer many of the questions that is in front of us, and so far we couldn't do it mathematically. So the concept of entropy will help us to give a mathematical statement for the second law of thermodynamics. Kelvin, Planck statement and Clausius statement are two wordly statements. Okay, it doesn't define any new quantity at all. But this entropy concept will help us to define in terms of a mathematical idea. That is why I told you that entropy is rather a mathematical device introduced by Clausius, right? And so let's see what are the different questions that we are not able to answer until then. So the questions like, you consider, suppose you have got an LPG cylinder, right? Okay, you have got a gas cylinder. LPG cylinder or some gas that is enclosed in a closed vessel, right? Consider an LPG cylinder, and if you open the lids of the cylinder, the gas inside the cylinder will be just escaping, right? It's not so the gas will be getting leaked to the surrounding. So that is the direction of flow of the gas, right? You never have seen, or you never have got reports saying that the gas which is spread to the surrounding is just coming back and getting by itself filled into the cylinder by itself spontaneously. So the first process, leaking of the gas, is a spontaneous process, right? Okay, but spontaneously never we see that the gas gets filled into the cylinder. Okay, there should be some extra work, outside work that is done to pump the gas into the cylinder. So it doesn't occur spontaneously. So why not? Spontaneously it is happening. Okay, that's one thing. Like I told you, the cooling of a cup of tea. Now another example you all have learned, or just you have noticed that in several cases you have a beaker and you fill with water. You say, see, this is water filled with and you drop a drop of ink into it. This is not a drop of ink is added to this water. What happens to that drop of ink? That the drop of ink will be getting mixed up. It's just some sort of a diffusion between two liquids. It gets, as time passes, it gets mixed up, and that this is somewhat you can just see that this is something like it happens spontaneously, right? Without any external trigger. The diffusion of this liquid into the other liquid is happening spontaneously, and even if you wait for long, you will never see a point when the liquid or the ink is just reversing its process. Means what? It's once again becoming a drop, right? So the mixed or diffused ink will not come back to a drop again. So the spontaneous direction of flow is to get diffused. Why it happens? Why not the reverse happening? Okay, so that's a question. Like, or you can go for many other examples. Almost all natural phenomena will give you a lot of questions like this if you spend time on it. See, you consider that you have got a pile of paper, right? You are keeping a pile of paper, right? Say that you have got some 100 sheets of A4 sheet, okay, 100 sheets A4 paper, or some pile of paper. You keep it on a table. Let the wind come and let it shatter or spread all these papers here and there, right? So by due to the blowing wind, the papers are just see that it is spread all across in the room, right? So you wait for long, okay? Can you ever imagine that one particular instant, due to the wind, all these shattered papers are again getting piled up in the way in which it was there in the beginning? Maybe you will feel it's a bit crazy question, but the reality is that there actually is a possibility, right? Is it not? Because if a bunch of paper can get dispersed in any manner, why can't in one instant the spread papers are again getting piled up in the same way? You never observe it, or so far we couldn't observe this one. That's why you feel it is crazy. So the spontaneous direction of the process happening is to get spread it in the way in which it is there. So okay, if you want, you can say that initially it was in a perfectly ordered state, in the word of order, right? So I'm using the word order with a bit caution because it should not give you some misconcept. Okay, usually entropy is one of the most misunderstood concept in thermodynamics due to the use of the term measure of disorder. So the word order and disorder should not be misinterpreted. So don't misinterpret me when I use the word order here. So maybe this is one reason why people tell that entropy in the beginning was less and entropy in the last stage was more in the case of the paper pile. Okay, so we say that the paper was much ordered, papers were much ordered state, and as the wind has blown, it has gone to an unordered state, so the entropy has increased. Okay, so at the end of a process, the entropy will getting increased. That is what we see if it's a spontaneous process. So every spontaneous process will be resulting in the increase of entropy. That is what we are going to see now. So the quantity which decides the direction of a particular process happening or not was realized to be, and it was named as what is known as entropy. And you can have several other examples. You consider just burning of coal, some combustion process, some chemical reactions, or expansion of gas into vacuum, or see, maybe if you want some more crazy examples, like you are dropping an egg from a height. Okay, you are dropping an egg from a certain height, and see, it strikes the floor and gets shattered into pieces, right? So can you ever imagine the reverse process happening? Maybe see that this is the broken or shattered pieces, the shells of the egg is combining again and it becomes a complete egg. Okay, maybe you will feel I repeat that. Okay, why all these questions? Because remember, there are processes in nature that happens only in one definite directions spontaneously, and people have been thinking why the processes are occurring only in one specified direction spontaneously. And the query finally led to second law of thermodynamics, and in order to give a mathematical understanding for the second law of thermodynamics, people searched for a physical quantity, better a mathematical quantity, and the search ended with introduction of the quantity what is named as what? Entropy. And that was a brief introduction. And if you want more about entropy, you can say that like the internal energy, the entropy is also a state function. It's not a path function. Okay, we will just prove all these statements in the coming videos or sessions. So remember, entropy is a state function, and the most important characteristic of this quantity is that the entropy will be attaining a maximum value in the equilibrium state. Okay, and that should be this statement should be contemplated much more. So it's a entropy is a state function which attains a maximum value in the equilibrium state of a system, and that will be a quite interesting. Maybe there is a controversial statement to begin with. Why? Let me tell you. The common way of approaching entropy, as we have been doing that entropy, we prefer to remember it as a measure of disorder. So I told you there should be a word of caution here, measure of disorder. I will try to interpret this word later towards the end of this one, this module, or in the next module. So entropy, we usually regard it as a measure of disorder, right? So more entropy means more disorder. Should it not be like that? More entropy, usually we denote entropy by the letter S. Okay, more the entropy, more should be the disorder as per our idea. Like, and this particular statement says that a entropy is a state function. Of course, no problem. Okay, for every state there will be a particular value of entropy, or it is independent of the path followed. Doesn't matter. We don't have any argument over that. But it says that it attains a maximum value. It attains a maximum value in the equilibrium state. So, won't there be a some sort of a what do you say? There is a just a disagreement with our usual concept. What is the usual concept? By the word equilibrium, what do we have in mind? Equilibrium is very is not. You feel that equilibrium is a very ordered state, no? I usually feel like that. When we listen to the word equilibrium, it's just a situation where there are no turbulences. It's completely pacified. It's completely settled state where I should say that there should be some sort of good order, right? Is it not? We usually think like that way, I think. Is it not? But this particular statement says that whenever a system has achieved its equilibrium state, the entropy of the system will be maximum. And unfortunately or fortunately, we try to relate entropy with disorder. So this statement says that at equilibrium, disorder is maximum. Maybe that's a controversy now. In the equilibrium state of any system, entropy is maximum means we should be able to conclude that the disorder of the system is maximum. Okay, are you able to agree with that one? Or is it some problem with our understanding of the word disorder? And that is a fact. That's why I told you that entropy is one of the concepts in physics which is mostly misunderstood. ഏറ്റവും കൂടുതൽ തെറ്റിദ്ധരിക്കപ്പെട്ടിട്ടുള്ള ഒരു വാക്കാണ് entropy. Actually, it should not be defined strictly as a measure of disorder in the way it is done. Okay, and it was used the disorder, but the people who use the word disorder to define entropy didn't mean what we actually understood. നമ്മൾ മനസ്സിലാക്കിയ രീതിയിലുള്ള ഡിസോർഡർ അല്ല എൻട്രോപ്പി എന്നുള്ള കോൺസെപ്റ്റിനെ ഡിഫൈൻ ചെയ്യാൻ വേണ്ടി ഡിസോർഡർ എന്നുള്ള വാക്ക് ഉപയോഗിച്ചവർ ഉദ്ദേശിച്ചത്. But unfortunately, it happened that we related disorder with our word. Okay, see the literal meaning of disorder, and that is why we will be using a better term, than disorder, and that term is given here. That is known as multiplicity. So better than disorder, what you can say that entropy is a measure of the multiplicity of the system, multiplicity of the state, and that idea was given by Ludwig Boltzmann later. Boltzmann was the person who was of immense scientific caliber and mathematical caliber, who finally or very late gave a statistical or molecular interpretation for entropy. Entropy was thermodynamically defined by Clausius. That's what I have to tell you. And the concept of entropy was introduced thermodynamically by Clausius, But later there was a lot of mystery. Lot of mystery was there. It was something mystical. Okay, in the word entropy, there was a lot of lack of clarity in the definition of entropy thermodynamically. But later it was Boltzmann who gave a statistical interpretation for entropy, and it related to what is known as multiplicity, and that gave birth to a new branch of physics, what is known as statistical mechanics, and which is our module 5. So we'll devote a module for statistical mechanics, okay, in our course, and that was a very revolutionary branch. A revolutionary concept was given by Boltzmann, and I will tell you about the fate of Boltzmann when we begin with the next module. Okay, so he was a person who was misunderstood for long, ridiculed for long for his ideas and introducing the statistical interpretation and all that. So he's a man who was not recognized at his lifetime, but later, okay, maybe it is our curse that okay, we are supposed to use Boltzmann constant in every calculation of thermodynamics thereafter. Okay, so that's the one thing that I want to tell you. Now, one thing more, the time won't be enough if you begin to talk about entropy. As I told you that entropy is the supreme okay, concept. I should say that more fundamental than energy. Entropy is a quantity that is more fundamental than energy, which decides the direction of occurrence of a process. Okay, so one thing more is that entropy is a monotonically increasing function of energy. You will see that I am using a lot of mathematical statements whenever I talk about entropy. The reason is that entropy is not a real physical quantity like pressure, temperature, which you can sense directly. Okay, you can sense pressure, you can sense temperature, but unfortunately you cannot sense what is entropy. You cannot directly measure entropy. That's why I told you. That's why there is a lot of mathematical demanding mathematics whenever we discuss about the concept of entropy. It's a mathematical device. I told you. I didn't say that it's a physical quantity. Okay, you can use it, but better with caution. So it's a mathematical device. So it's a monotonically increasing. Monotonically means ever increasing, right? Okay, monotonically increasing means it won't show a decrease. The slope will be always positive. Okay, monotonically increasing function of energy. If the energy of the system increases, the entropy of the system also should increase. That is the meaning of monotonically increasing function of energy. Okay, and I told you that it acts as a bridge between the two branches of physics, okay, namely thermodynamics and the newly introduced branch, what is known as what? Statistical thermodynamics, or better known as statistical mechanics. Okay, so the connection between thermodynamics and statistics was given. It was possible by introducing the concept of what? Entropy. And in order to connect these two branches, Ludwig Boltzmann introduced a very famous equation, S equal to, you will see this equation, S equal, in the next module in detail, S equal to KB log of W. KB log of W. Okay, where you know this on the left side, S is entropy, KB is the famous Boltzmann's constant that we have already seen in our equipartition law, and W is what is known as multiplicity of the state. Multiplicity of the state, which we were telling about something as disorder and all. Okay, so W, S equal to KB log omega, and this is what is known as the famous Boltzmann's equation for entropy. And it was for this equation Boltzmann was ridiculed and criticized by many of his contemporary scientists for a long time. And the cost of this equation was the life of Boltzmann. You will see that Boltzmann committed suicide finally due to desperate comments from his fellow beings, and in order to show the importance of this equation, the history of the life of the scientist, great scientist, as well as in the birth of the statistical mechanics. You will see that in the tomb of Boltzmann, Ludwig Boltzmann in Vienna, Austria, this particular equation is written. Okay, maybe you know that we'll be writing RIP son of or born and died on certain dates and all, usually in our tombstones. But in the tombstone of uh, Ludwig Boltzmann in Vienna, this equation has been inscribed, and it's a very see just catchy photograph. You can just search in Google for this photograph. It tells you about that people have loved something in their life to that extent that it becomes a part of their life even after their death. So whenever you talk about the word entropy, I want you to remember that people have given their life for defining and trying to understand, trying to just focus on this quantity, and that was a kind of devotion that was shown by people like Boltzmann and many others. So I wanted to mention that the topic that we are going to see in this particular module has got a lot of relevance, and we have devoted an entire module for this one only because of its relevance. And we'll try to try to be with me, try to just read the material. I will be just uploading the reference material for you, reading material as a notes, so that you can just go on making the notes along with. All right, so to conclude this particular session, as I told you that the entropy is one of the thermodynamic variables similar to pressure, volume, temperature, internal energy, but of supreme importance. And by introducing the concept of entropy, we could develop a mathematical statement for the second law of thermodynamics, and thereby we can just explain in which direction a particular process will occur if it is left to itself or by spontaneous things. And we will finally conclude with the at the end of our module, we will conclude that in every naturally occurring processes, the entropy of the system will be will be either increasing or will be remaining constant. It will never decrease, or the entropy of the universe will be always going on increasing, and that is what is known as the principle of increase of entropy. Entropy of the universe will be always going on increasing, and it will finally relate to the arrow of time. So remember, that is one important statement that I am making here. The direction of increase of entropy gives the direction of arrow of time, whether it is yesterday or today, whether it is today and tomorrow, or tomorrow and day after tomorrow. You can just find out. If you are after a long sleep, you have to understand whether it is yesterday or today. The thing is that you just compare the entropy on the 2 days. If the entropy is more on one day than the other day, then the day which comes after will be having more entropy. Means entropy of today will be more than that of yesterday. I am talking about the universe as a whole, the physical universe. Entropy of the universe today will be more than that it was yesterday. Entropy of the universe tomorrow will be more than it was what today, and entropy of the day after tomorrow will be more than it will be tomorrow. So the entropy of the universe will be ever increasing. Remember, I am using the word universe. Universe here is a physical universe, and that is what is known as the principle of increase of entropy. We will be elaborating on those things also in the coming sessions. So be prepared. We will meet in the next session. Thank you.